Hey everybody, here is another question. This is an AP Physics C question actually from 2004, but it doesn't have any calculus in it, so it's a good practice here. And this one's got it all. It's got conservation of energy, conservation of momentum, horizontal projectiles, centripetal motion. So it is a good review question of a lot of stuff that we've covered up to the momentum unit here. All right, very first thing, to summarize what they're saying here, we got a person of mass m1. They're holding onto a rope of length L. They swing down so that they just scrape above the surface here. So, and they even kind of indicated here, that means that this height here is also L. So they're on an L high ledge. They swing down here. There's an object down there of mass m2 that they pick up while they're swinging. So they grab that thing, and then immediately also they let go, and then they fall off here, and they go do, and they land down in the lake down there at point D. By the way, this second cliff is also height L as well. So now let's find out some of this information that they're asking for. They say, what is the speed of the person just before the collision with the object? So they swing down here. What is their speed right there? So this is a conservation of energy question. We had gravitational potential energy sitting up on that ledge, and it's going to become kinetic energy as we swing down there. Now, let's plug in for each of these. Gravitational potential energy is mass times gravity times height, and kinetic energy is 1/2 times mass times velocity squared there. The masses cancel out here, and we get an equation that we are used to seeing a lot if you've memorized this, which you should, that the velocity is equal to the square root of 2g. We'll replace the height here with the L, so that is what they're calling our height. So our velocity, just when we get to the bottom here and we strike the second object, our velocity is the square root of 2gl. Now, let's go on to part B here. So on part B, they say determine the tension in the rope just before the collision with the object. All right, this is a uniform centripetal motion problem. We are down here. We are swinging this way. So the tension is up here, and the force of gravity is down there. Now remember, the way we set these up is we say this, that the sum of the forces is equal to a centripetal force since we are going in a circle. So let's think about what we have to add up for our forces. We have tension towards the center and the force of gravity away from the center. And that will equal centripetal force is mv squared over r. I'm going to keep all this generic until the very end there when I plug in. All right, so now let's start to solve this like we're doing just a normal centripetal problem. Let's add the Fg to the other side. So tension equals, and I'm also going to substitute in for Fg is mg plus mv squared over r. Now we're ready to start doing some substitutions that are particular to our problem here. So the tension now is equal to, this m is the mass of the person, which they're calling m1. So m1g plus m1 again here. Now v, this is our v from before. This is our square root of 2gl. Our v is getting squared. So this square root goes away, and we get 2gl. And all of that is over top of our radius. What is the radius of our circle we're going in? It is also L, because our rope is length L as well. So L goes right here. You can see that our L's here and here cancel out, and then it simplifies down to something nice and neat in the end. Our tension is equal to, since we have m1g here and 2m1g here, it winds up being 3m1g is our tension at the bottom there. Okay, so now let's do the next part. C says the speed of the person just after the collision. So they're going to swing down here, and they're going to pick up this extra mass. When you have a collision, that's your key word there, that is conservation of momentum. So conservation of momentum here. So the momentum of our system in the beginning is equal to the momentum of our system afterwards. So in the beginning, we have the person moving, so that's m1, with some velocity of the person. And I'm going to plug in for that later, but I'm just going to call it v1 right now. So afterwards, the person picks up the object. So it's m1 plus m2, and we're going to be looking for that velocity afterwards there. So now, let me sort of plug in for these. This velocity right here, you can see we're just going to divide this down to the other side here. And all I have to do is plug in that particular velocity. So solving for v here, we get m1. Now our v, if you remember, is the square root of 2gl. And that goes over top of this whole term here, which we divide down, m1 plus m2. So using conservation of momentum as our guide, that is the velocity of the person and the object after the collision. All right, now, next part here. They say find the ratio of the kinetic energy of the person object system before the collision to the kinetic energy after the collision. All right, so our kinetic energy initially over our kinetic energy in the end. By the way, we know that this number is going to turn out to be something that has to be greater than 1, because when we have a collision where things stick together like that, then that is an inelastic collision, and therefore they must lose energy. But let's prove that here. So this is going to be 1/2 times the mass of our person times that person before they hit velocity squared. I'm going to plug in for that specifically later. And then our kinetic energy afterwards is 1/2 times the combined mass of the person and the object times their velocity. Let's call that v1 prime, or v prime squared. All right, now let's start to plug in for some of these. So, by the way, the halves here cancel, and we get m1. Remember, right before the collision, the person was going square root 2gl, but that gets squared, so we wind up with just simply 2gl. All right, down here, we've got m1 plus m2, and the velocity of them squared. This is the velocity after the collision. This is where this one starts to get really messy. So here's the velocity after the collision, all of this. We've got to take all of this and plug it in for this v, and we got to square it, right? So here, let me write this down here, and we'll clean the fraction up later. The m1 part gets squared right here. So m1 squared. The part right here, the radical gets squared, so that just goes away and becomes 2gl. And then the bottom part here gets squared. So that is m1 plus m2, all of that squared. Let's clean this up a bit. I'm going to flip this fraction, and you'll see in the end it doesn't wind up being that bad. Since we're dividing by this fraction, it's the same thing as multiplying by its reciprocal. So we get m1 2gl from this part over the quantity m1 plus m2. So I'm just keeping what was written in purple right here. Now let me flip what was written in green. m1 plus m2 squared, because we're multiplying by the reciprocal, over m1 squared 2gl from here. So I just flipped some multiplying by the reciprocal. Now you'll see this actually simplifies down a lot. This 2gl cancels out with that 2gl there. This m1 squared, so this m1 cancels out with one of those m1s down there, and likewise this m1 plus m2 cancels out with one of those m1 plus m2s there, and in the end we get something not so bad. We get m1 plus m2, all of that over top of m1. Man, that is a lot. But let's think about again what I originally said. Here we have some bigger number. Here's something, m1 plus something over m1. So this number is bigger than 1. We would expect that for an inelastic collision. In other words, we'd expect the initial kinetic energy to be bigger than the final kinetic energy, because we know in an inelastic collision that we lose energy to heat and sound and deformation and things like that. All right. One last part here. So it says, find the total horizontal displacement x of the person from position A until the person lands in the water in position D. So from their total x here, if you look in the bottom, the total x from A to D. Well, look, right here they move L. Right, we see that. They move L to get to the side here. So this platform is also L, as they indicated here. So now we need to find this distance here. This is a horizontal projectile problem. So let's find this distance right here from this wall to D, and then we'll add in L in the end there. So to start to do this, we need to do a horizontal projectile problem. So again, we need to find the time to fall. So use the third equation. The vertical displacement is equal to the initial y velocity times time plus 1/2 times the vertical acceleration, which is g times squared. There is no initial y velocity, so when we solve for this, the time will simply wind up being 2 times the height, and the height, remember here, of this ledge is L. So 2 times L over g is our answer there. All right, that's our time to fall. Now, we got to think about how far we're going to go to the side. Now, what do you want to call this? You might call this our delta x as we go from point, what do you want to call it here? Our delta x, just this section right here, so not the entire x. So maybe call it something different. I don't know what you want to call it, d, let's say. Not point d. Anyway, all right, let's solve for this. We're just solving for the movement during the horizontal projectile part. That is going to be our horizontal velocity times our time. So now let's plug in for that. So we're going to use the third equation here. Again, this, you can just think of our distance as our constant velocity times time, or you can think of it as the same equation here. It's just this time there's no horizontal acceleration. So plugging in here then, our distance we're going to travel, our horizontal speed, that is our speed that we left after the collision, this big mess right here. So m1 times the square root of 2gl over top of m1 plus m2. So, and we're going to multiply that speed times our time, which is right here. So square root of 2l over g. Now some things are going to simplify and come out of the equations here. So one thing is we got a g down here in the bottom, in the denominator of under a radical, and we have a g there in the numerator under a radical. The 2l's are going to come out because we have two 2l's underneath a radical. So we get 2l, that's everything underneath the square root. So we have 2l times m1 over top of m1 plus m2. Now that is the distance we travel during our horizontal projectile part. So if we actually want the total distance, we've got to add on there our sideways distance that we traveled before we became a horizontal projectile, which was simply L there. Man, that is a mess. They don't mess around with their fractions in AP Physics C.